Assalamualaikum and a very good day. Okay, today we will go into the third chapter of biomems, which is the micropatterning of the substrates. Okay, for the second slide, we will go into the overview of the fabrication, how we are going to fabricate on the macro or micro scale, okay, using the self-assembly monolayers, where we can divide this method in two separate methods, which are top-down. Okay, small sections of a large substance are removed. Okay, if you still remember about the first chapter, okay, about the surface micro machining, okay, what we do there is that we remove a small section of the bulk substance. Okay, another one is bottom up is like you're playing with a Lego. Okay, the designs are created from scratch by assembling together different building blocks. Okay, just like when you are playing Lego. Okay, so now, okay, for this particular chapter, we will see about this bottom up fabrication. Okay, the versatility and creativity of the bottom up method, okay, has great potential in microtechnology and also nanotechnology. Here we need to understand, okay, how to manipulate the factor, okay, which allows self-assembly to happen. Okay, there are four factors, okay, which are electrostatic forces, hydrogen bonds, okay, dispersion forces, and also hydrophobic effects. Okay, so electrostatic forces, okay, the Coulombic interactions between positive and negative charged particles. Hydrogen bonding, okay, bonding that involves a hydrogen proton donor. Okay, you can refer to the previous topic, okay, about the hydrogen bonding. Dispersion forces, which is also known as London forces, okay, manipulating the weak dipole. These dipole forces are present in and between all molecules. Okay, and the last one is hydrophobic effects. Okay, non-polar bonding in an aqueous solution. Okay, so these four factors okay, are the things that allows the self-assembly to happen. Okay, for the fourth slide, okay, this slide is about the characteristics of SAMs. Okay, the self-assembly molecules thickness, okay, is only about a few molecules thick. Okay, few molecules thick. You can refer to the right figure. Okay, this is how does it look. Okay, it is formed by reactions between surface and surface active molecules. Okay, and this is one of the application. Okay, give macro surfaces an entire substance the properties of the same properties by only adding nanometer thick surfaces. Okay, so one of the example is that, okay, implants can be coated with surface layers that are biocompatible. Okay, one of the closest example, okay, for this is like you coating, okay, coating your jewelry with gold. Okay, your maybe the main material is maybe normal metal. Okay, normal metal, normal ferrometal. Okay, normal iron. Okay, but then you coat it with gold. You coat it with gold. So okay, by just coating your jewelry, okay, you get that although it's not as valuable as the original jewelry made from gold, okay, but the function is the same. Okay, the function is the same. Okay, and then there's another diagram on your left side. Okay, you can see that the polymeric, okay, assemble monolayers. Okay, so it doesn't have to be one particular layer. Okay, it can be random. Okay, it can have a block side. Okay, it can be like just one or two grafting. Okay, but these layers have their function. Okay, slide 5, okay, shows an easy example of SAM fabrication. Okay, you have a solution of surface active material, then you add up it with the substrate. Okay, you immerse the substrate with the solution of surface active material, and then after that you will get a closely packed ordered SAM. Okay, so the driving force for the surface aggregation and self-assembly is the covalent bond formation of the film molecules, okay, with the substrate surface via suitable functional groups. Okay, so you need to have, first of all, okay, you need to have a suitable functional group first, okay, so that it can attach, okay, the molecule can attach to the substrate. Okay, and then you have the intermolecular, okay, inside the molecular, the van der Waals type interactions between the hydrocarbon chain of the film molecules. Okay, this slide, okay, shows two methods of how to make a SAM. Okay, first is electrostatic self-assembly. Okay, it utilizes the electrostatic interactions between the molecules. Okay, so this is one example using the photo switch wettability on an electrostatic self-assembly azobenzene monolayer. Okay, another one is layer by layer method. A surface is first modified so it can bear different charge groups of particles. Okay, the surface is then dipped into a solution of an oppositely charged solution. Because of electrostatic properties, the solution bonds uniformly onto the entire surface. Okay, multiple layers can be added to the surface by alternating the charges on each subsequent layer. So this is just like an example, like a previous slide. Okay, on this slide 7, okay, it shows the block copolymer self-assembly. Okay, so by manipulating polymers at the molecular level, okay, we can modify their behavior to bond, break, or stack in deliberate pattern. So we know different type of interaction. Okay, chemical interaction, we just manipulate it, and then we have a different type of block copolymers. Okay, so different, like for instance stripe, this represent a different type of monomer that have been changed into a certain type of polymer. Another one, then you can see the same thing for the island. Okay, another one is using microphase separation. Okay, when two polymers are forced combined to form a copolymer, okay, they will inherently try to separate from each other. This is also one of the strategy that we can use. Okay, by manipulating intrinsic property, scientists can cause block copolymers to form many different shapes and surfaces. This is one of the good example. Okay, so this is how we fabricate a self-assembled lithium battery. Okay, we have a few layers there. Is a polyethylene oxide, PO. GO is a graphite oxidized by nitric acid, or nitric acid, or natrium NaClO3. Okay, another one is the PDDA. So this is how a type of a self-assembly molecules being manipulated, and you can see how it's being used. It's being used in practical. It's not only in theory, but it's also a practical things that have been used for some times. Slide 9 is a good example of one self-assembled monolayers. Okay, one monolayer is represented of all the functional group. Okay, the head group and so on. Okay, so in the past, okay, I had ask this in the quiz. Okay, ask this in the quiz about how does the layer is made from. Okay, one layer is made from, like for instance, we have the metal substrate. Okay, and then you have the ligand or the head group, and there's a metal sulfur interface, okay, which stabilizes the surface atoms. Okay, it also may modify electronic states, depends on what type of application you are using. Okay, then you have the spacer, which may made from the alkane chain. Okay, and this also acts as an organic interface, okay, which is just like 1 to 3 nanometer, okay, the size, okay, and the length, okay. It provides well-defined thickness, okay, acts as a physical barrier, okay. It alters electronic conductivity and local optical properties. Depends, it depends, okay. Like for instance, if you are using it to improve biocompatibility instead of altering the electronic conductivity or electrical conductivity, okay, it may improve the biocompatibility of the surface. And the last one is the terminal functional group, okay. It depends, okay. Sometimes maybe you are planning to make another reaction, okay, to improve the surface, okay. You want to add another chain or another functional groups, okay. So but the last one is the organic interface, okay. Let's say if you don't intend to make another reaction, and this is on the only layer that you have, okay, and this final functional groups, okay, will determine the surface properties. For instance, the biocompatibility and so on, maybe like the wettability, okay, and other properties that is important in your, okay, for your application. Okay, so for slide 10, this is just about the application of the SAMs. So it can modify the wetting properties, okay, by selective addition, okay, or by the biofunctionalization. Okay, you can see that, okay, it may change the hydrophilicity or hydrophobicity of the surface, okay. One of the application is in the for reading the hard disk, okay, and it can be used for lubricants for hard disk, corrosion protection, photo patterning, electronic devices, okay. So this has a lot of application actually. So this is where, if you know, okay, how to manipulate SAMs, okay, you can use it for many type of biomedical applications. Okay, slide 11 is important, okay, in terms of, okay, how do you relate our lithography with SAM, okay. So this is how you put your self assembly of biomolecules on on your MEM substrate, okay. So first of all, okay, you have your photoresist or your e-beam resist or something, okay, and your substrate. Then you do your e-beam lithography, okay. Let's say if you want to put it in the nano, especially at nano size, okay, nanometer size, okay. So you have your e-beam lithography, okay. You expose it to your e-beam, okay, and then you do your development, okay. Then you do your oxygen plasma. Why? Because you want to modify your surface, so you can have your first self-assembly molecule to be on your substrate, okay. Then you have, okay, if you see the blue, okay, the blue molecule, okay, so that will be your first layer, okay. Then you will have, okay, then after that you remove another resist, okay. Maybe you use stripping, okay. Then another one, okay, then you do your reaction, okay. You do your reaction, and then you have your second self-assembly molecule on the substrate. Slide number 12 and 13, okay, should be referred together actually, okay. Okay, there are a few ways of grafting molecules or biomolecules, okay. So I would like to introduce you in terms of polymerization of the of these biomolecules using two types of technique. First of all is the grafting from, another one is the grafting through. Okay, in this slide, okay, I will give the definition and also the advantages and also maybe the disadvantages of each of the technique. Okay, grafting from synthesis of molecular brushes. Okay, now you just imagine like you want to make a molecular brushes. Okay, starts with the preparation of the backbone polymer. So you have the backbone polymer, okay, with a predetermined number of initiation sites that is subsequently used to initiate polymerization of the side chain. So you have the backbone first, okay, and then it has a micro initiator that will determine the number of the initiation sites, so that there will be interaction. Okay, you can grow you can graft from the backbone. Okay, in grafting from, okay, via control radical polymerization, okay, technique, a low instantaneous concentration of radical species necessarily limits the termination events. Okay, so this is the advantage. So the advantage of using this technique is that you can limit the termination events, okay, because intramolecular termination can lead to pendant microcycles, and more importantly, intermolecular coupling can lead to microscopic gelation. Okay, as such, the grafting from, okay, technique will approach will enable the preparation of long backbone molecular brushes with a high grafting density and a narrow molecular weight distribution. Okay, but however, okay, if you compare to the grafting through approach, grafting from, okay, allows less control of side chain length and grafting density. Okay, slide 13 is an easier way to understand how the grafting from technique is used. Okay, you have a monomer with a functional group, then you build the backbone using ATP, atomic transfer radical polymerization. Okay, so after you have built built your backbone, okay, you have determined the length of your backbone. Okay, you do the side chain, okay, polymerization. Usually you may be using the ROP, depends on what type of a monomer you're going to use, and then you can have your graph polymer there. Okay, slide 14 shows us the grafting through technique. Okay, grafting through technique is like, okay, just now grafting from is about making the backbone first, and then you grow the leg. Okay, now we make the leg first, and then we combine the leg to make the backbone. Okay, so the grafting through route involves the polymerization of micromonomers through their terminal functionality. Okay, perhaps the most attractive feature of this method is that each repeat unit of the backbone contains a covalently bound side chain. Okay, also because the micromonomers are prepared separately, the side chains can be characterized prior to polymerization. Okay, so you will allow the preparation of brushes with well-defined grafting density and side chain length. Okay, so here are some of the definition. Okay, TRP is atom transfer radical polymerization. Okay, ROP is for ring opening polymerization. Okay, slide 15 shows you the grafting through technique. Okay, you have the monomer with terminal functionality. Okay, then you do your ROP, okay, ring opening polymerization for the side chain monomer. Okay, and then you can see that you have created a macromonomer. Okay, this macromonomer you will do ATRP. Okay, and then you will have your graph polymer. Okay, slide 15 shows you some other grafting strategy. Okay, we have also grafting 2. Okay, apart from the grafting from and grafting through techniques. Slide 17, we just do some revision on the polymers. Okay, so polymers are referred as macromolecules, okay, due to their gigantic size. So it will be very huge molecules. Okay, the molecules are in the form of long and flexible chains. Okay, so monomer means one mer. Okay, polymer means many mers. Okay, mer originates from meros. Okay, so polymer means many parts or monomers. Okay, this monomer, okay, before becomes a polymer, okay, refers to stable molecule where the polymer is synthesized. So you have few types of polymer shown here, which is a polyethylene. Okay, the polyvinyl chloride and also polypropylene. Okay, so the mer for the polyethylene is a C2H4. Okay, C2H4. Okay, polyvinyl chloride, we have one chlorine. Okay, instead of having all four is hydrogen, okay, you have one chlorine. And then for polypropylene, you have one CH3 there. Slide 18. Okay, we classify polymers into three major classes, which are the fibers, plastics and elastomers. Okay, so the table shows you the properties of polymers. Okay, about the upper limit of extensibility. Okay, character of stress deformation, crystallization tendency, and also the initial Young modulus. Okay, so popular polymer under plastic classifications are polyethylene, polypropylene, okay, PVC, and also polystyrene, fluorocarbons, epoxies, phenolics and polyesters. Okay, so sometimes, okay, the manufacturer will add some other chemicals to improve the physical, chemical, even electrical and thermal, and even the biocompatibility characteristic. Okay, to achieve what type of polymer they want to have for their product. Okay, slide 19 shows us other type of classification, whether we want to classify them as natural polymers, okay, or synthetic polymers. So we can say even the natural polymers consist of silk, rubber, cotton. Okay, for synthetic polymers, usually we make them using petroleum products. Okay, other classifications may include the response of the polymer to the temperature. Okay, thermal plastic polymers. Okay, we can remelted the polymer and then shape it repeatedly. Okay, and then maybe another one is that thermosetting polymers. Okay, so you just melt it once. Okay, you have a one permanent shape once you have processed it. Okay, so for polymer, especially if you want to use it for biomems, okay, you could consider it as a you can consider it through the Young modulus. Okay, some have a strength, okay, like several megapascal, sometimes up to gigapascal. Okay, others is like in the order of 100 megapascal. So it is lower than the metal and semiconductor. Okay, so many of these polymer exhibit the viscoelastic behaviors. Okay, and then the mechanical properties are influenced by temperature, molecular weight, additives, degree of crystallinity, and also heat treatment history. Okay, so for now, okay, researchers have already the researchers have conduct many researches, and for now, okay, the polymer electronic devices are not able to compete with semiconductor electronic performances. Okay, slide 20 is the technique that you can use to deposit thin polymer films on your substrate. Okay, you can deposit your polymer materials by using spin coating, vapor coating, spray coating, and electroplating. Okay, so here polymers can serve as such layers and provide unique mechanical, electrical, and chemical characteristics which are not available in semiconductor films. Okay, and because of polymer is easy to be removed by using solvent, you can remove them by dry etching or by using strong organic solvents including acetone. So slide 21 shows a schematic diagram of a method for forming pattern PDMS. So you apply the photoresist, and then you do the you apply the PDMS. Okay, so you start to pattern it. You pattern it, and then finally you remove the photoresist. Okay, and then you have your PDMS on your substrate.